Hello friends, welcome to my channel. Today we are going to see very interesting topic, and that is losses in a transformer. Okay, to start with, why do we need to measure transformer losses? Transformer play critical role in transmission and distribution system. The real cost of a transformer for the owner is the sum of initial purchase price plus cost of running for lifespan around 30 to 40 years. Purchasing decisions requires the right balance between the initial purchase cost and cost of future losses. Losses are the wastage of energy in the device which will affect the overall efficiency. Transformer life cycle cost is a consist of purchase cost that initially need to bear, cost of losses, no load loss and load loss throughout the lifespan, commissioning cost, maintenance cost, cost of out time reliability. Reduction of energy losses and related cost normally leads to higher initial cost. For better understanding, we just took one transformer, typical transformer, rating plate of a typical transformer, and we found out this 500 kVA transformer having full load losses around 7000 watts and a no load losses 1100 watts. So let's find out what are the different losses and how these losses are contributes towards the life cycle cost of a transformer. There are four types of major losses in a transformer. Iron loss, also called as core loss, copper loss or ohmic loss, stray loss, dielectric loss. Iron loss has two types, hysteresis loss and eddy current loss. Red color indicates approximate percentage of the losses. So maximum loss occur is copper or ohmic loss. For a better understanding, we have created a simple template. Losses, where it occur, why it occur, when it occur, what are the effects, how much in percentage, mathematical equation, method to reduce, and actual test. Hysteresis loss are the fixed losses. It happen in core magnetic material due to cyclic magnetization of the core. It occurs every cycle of alternating magnetic flux. Effect is heating of the core 2 to 3.5%. It varies transformer to transformer and its application. Hysteresis loss is equal to Kh multiplied by F multiplied by Bm raised to N, where Kh is a constant of material, F frequency, Bm maximum flux density, and N depends upon material 1.5 to 2 is the range. So hysteresis loss is directly proportional to frequency and directly proportional to the maximum flux density. As flux density increases, losses will increase. Flux density related to volts per ton and volts per hertz. How to reduce hysteresis loss? By using low loss CRGO material for the laminations. Use adequate cross section of the core. Use lower hold per turn and holds per hertz during design. Purity of waveform. Eliminate harmonics by using filter. Avoid saturation of the core. Proper path for zero sequence current. By a no-load test, we can measure hysteresis loss. Eddy current loss occur in conducting material in the alternating magnetic field. Eddy current loss in core laminations happen because of eddy current when conducting material subject to the alternating magnetic field. Effect is a temperature rise. Losses around 2 to 3.5% of total losses. Mathematical equation: eddy current loss in core lamination is equal to Ke T square Bm square F square divided by rho, where Ke constant of material of the core, Bm peak flux density, F frequency, rho electrical resistivity of material of a core, and T thickness of a lamination. How can we reduce eddy current loss in core lamination? Provide insulation layer on both sides of lamination. Reduce flux density. Reduction in leakage flux. Increasing resistivity of material by alloying with silicon. By no-load test, we can measure eddy current loss. Now we'll see eddy current loss, that is fixed losses in conductor. It happened because of eddy current when conducting material subject to the alternating magnetic field. Effect: it will cause a temperature rise. The contribution is around 2 to 3.5% of total losses. Mathematical equation: eddy current loss in a conductor or in a coil is directly proportional to KCE B raised to 4 N raised to 2 F raised to 2 beta divided by rho square. B is a radial dimension of a conductor, direction perpendicular to the axis. F is a frequency. Beta is a factor which takes into account the cross section of a conductor and total cross section of the coil. Rho is electrical resistivity of material, that is conducting material, and number of conductor in radial direction. How to reduce this eddy current loss? By subdivide into strands or parts insulated with each other. Transpose conductor to minimize circulating currents. By using a no-load test, we can find eddy current loss. Stray losses. Stray losses are the variable loss. It occurred in tank, clamps and other metallic parts due to leakage flux and permeability of a material. It occurs when current passing through the winding, high current loops outside the winding. Effect: source of heat generation, paper insulation loses its insulation property. Its losses contribution is 10 to 15%. It's very complex to find the stray losses. FEM based analytic techniques are used to reduce the stray losses. Reduction in leakage flux, non-magnetic material in a closed path surrounding conductor. Cut the closed path, additional shield near to the tank walls. By using no-load test and short circuit test, we can find out stray losses. Next losses is ohmic or load loss, which is a variable loss. It occurred in copper windings. It occurred due to a loss used by transformer winding electrical resistance when a load current flows. It occurred during a load current flows. Effect is higher hotspot temperature and higher oil temperature. These losses contribute 70 to 85% depending upon the load. Mathematical equation PL equals to I square R. So, ohmic or load loss is directly proportional to I square. It varies along the load. That means is directly proportional to the resistance, and resistance is proportional to the temperature. So we can say that the total losses is equal to, that is total ohmic loss is equal to primary side I1 square R1 plus secondary side I2 square R2. How to reduce the ohmic or load loss? By using appropriate design of the winding, reduce length of winding and a winding in parallel path, reducing resistance of the winding. By using short circuit test, we can measure load losses. Next one is a dielectric loss. Dielectric losses are occurred in insulating material of a transformer. When the oil gets deteriorated or a solid insulation get damaged. It occurs during a loading and a no-load condition of a transformer. The more tan delta increase, dielectric losses and increased more and more temperature until thermal breakdown occur. These losses usually negligible. A dielectric loss is equal to 2 pi f c v square tan delta, where f is the applied frequency, c is a capacitance in farad, v is operating voltage in RMS, tan delta is a dissipation factor. Dielectric losses are proportional to the tan delta. As the temperature increases, tan delta and the losses are increasing. How to reduce this dielectric loss? By using periodic testing method of oil, and maintaining the insulation quality is an effective way to reduce dielectric loss. By using a tan delta test method, we can find out these losses. Okay, let's recap. So far we have studied different losses in a transformer. Core loss or iron loss, which consists of hysteresis loss and eddy current loss. They are the fixed losses. Copper loss, stray loss and dielectric loss are the variable losses. For further study, we took 5 types of transformers. Transformer manufacturer A, B, C, D and E. The rating is 500 kVA and we compare different losses. So we found out transformer D having highest number of no load losses, 1600 watt, while transformer B having highest number of load losses, that is 7000 watt. Okay, I hope you like my video. If you have any questions, please let me know, and please do like, share and subscribe to my channel. Thank you.